Welcome, ladies and gentlemen. So if you've noticed one thing with our optimization problems, hopefully it's that we're kind of upping the ante here in our BC curriculum. Such is the case with today's Bellwork, and I thought that while working together, right, you could kind of talk it out and come up with a strategy. Let's go ahead and see how that's going. So let's suppose you asked to find the dimensions of the right circular cylinder of maximal volume that can be inscribed in a sphere of radius 10. And what is that volume? So I went ahead and drew a picture here. And I think the key is being able to determine, right, how the dimensions of that cylinder, right, are determined by the set radius of the sphere. We're still going to use our same strategy, though. I need direction for the problem. I need a goal. So what is my goal? What am I trying to do? Courtney?
Maximize volume.
Good. I'm trying to maximize volume. So that's going to provide my focus, direction, and goal for the problem. That's going to be the formula that I write. That's going to be the function that I write. That's going to be my function I differentiate with my first derivative test, etc. So we're trying to maximize volume of the cylinder, right? There's my goal. All right, let's go ahead and write a formula then for that volume. In order to do that, we need to go to our picture. So, and I think the key here is recognizing that the center of my right circular cylinder and the center of the sphere rather coincide. And so here in the middle, right, that center in the middle of my sphere and right circular cylinder is the same point. Yes? And I know that the sphere is of fixed size, and so it's always a radius of 10. If I can connect this center to the edge of the right circular cylinder where it touches the edge of the sphere, right? That's the inscribed portion. I know that that's set, right? That's a set dimension. What is that set dimension? Sophia? 10. That coincides with the radius of the sphere. So I can label that with a constant because it's not changing, right? It's not changing. It's set at 10. What is changing? Well, the height of this right circular cylinder and the radius of this right circular cylinder are changing. So I'm going to need variables for those. But right now, I'm going to go ahead and construct a right triangle. If I can make a right triangle in here, I can utilize all those relationships that we know from a right triangle, like SOHCAHTOA, Pythagorean theorem, all that. All right, so let's go ahead and see what I need from that right triangle diagram and what variables I need. Again, I'm trying to maximize volume, so let's go back to my volume of the circular cylinder is given by V equals. And what's my general formula? No X's or anything like that. Just in general, what's the formula for the volume of a right circular cylinder? Brendan?
Pi r squared height.
Pi r squared times the height. Absolutely. So let's go ahead and get those and see if we can't find any of that in my problem. In my problem, I see the radius of my cylinder is this horizontal line segment. Yes, so I'll label that R. There's my R. And the height of my cylinder is not this leg length, right? It's what? Well, it's double that. Yes, it's double that. And so I'm going to keep that in mind when I go and try to rewrite that as a function of a single variable. Back to my triangle. What's this leg length given by, though? I mean, what's this leg length given by? Riley?
It'd be the, well, okay, so it'd be the side inverse of the...
Just with the right triangle, we have two sides. I mean, yep, the square root of 10 squared minus I squared is this dimension, right? Well, we could simply double that then to get the h in my problem. And so I think we're ready to start doing with our r's and with our h's. This leg length right here of my right triangle is given by the Pythagorean theorem. The square root of 10 squared minus r squared equals that red distance, yes? So twice that red distance would be the height h in my original volume formula. And if I like working with x's, right, if I like working with x's, I can go ahead and call this x right now. Then this will be x, and my height will be twice that radical 100 minus x squared. All right, so let's go ahead and rewrite my volume formula as a function of one variable. Here we go. V of x equals pi x squared times, and what's my height? Well, my height is twice that radical 100 minus x squared. You guys see that? That's my height. And so I just needed 2 root 100 minus x squared. That's pretty bomb. Great. So I'll do a quick rewrite, and I'll be all set to go with my closed interval method. If I can get a domain, my first derivative test, my second derivative test, whatever seems to make the most sense. But first I'll go ahead and rewrite this one more time. So maybe a 2 pi x squared root 100 minus x squared. How's that? Pretty good? Let's maximize that. Do I have a closed interval? Right? Can I consider the domain of my function now that I've written in terms of one variable? Well, kind of. I mean, 0 for my radius would obviously produce a right circular cylinder of 0 volume, right? And then if I let my radius continue to increase, it would clearly be bounded by the edge of the sphere. But then again, it would just be a flat disk, and so that would have 0 volume too. And so you could make the argument that, yeah, we could go 0 to, what, 10, right, and have a closed interval. Or we could still want to do the first derivative test so that I can see the sign chart and be confident that we've reached a max. All right, so I'm going to go ahead and differentiate. This is where the excitement really begins. And so we need to differentiate this mess. Can we do that? Yeah, we can. What rule will we have to use overall? A product, because I have x appearing in multiple functions. We're going to have to use the product rule. So I'm going to go ahead and let this be my constant out front. Did you guys do that as a constant out front and then do big parentheses? Gosh, Mr. Fritz, those are big parentheses. Well, I know I'm going to have to do a sum there, and I've got kind of a nasty function with the radicals. So here we go. The derivative of the first function times the second plus the first function as is times the derivative of the second. And as you guys do more and more of these, you know the derivative of that square root function is 1 over 2 times the square root function times the derivative of the input. The input in the square root function itself is negative 2x. The square root was 100 minus x squared. And I know I saw some people differentiating. Is that what you're getting for that derivative of that radical function? Is that what you're getting? Yes? All right, let's go ahead and make that look prettier. Okay, so let's take care of the 2's. Let's keep this 2. And are you guys probably not ready to make a common denominator yet? I'll just leave it like this first. And we'll make this minus x cubed over root. Are we okay? And now I'm going to go ahead and make a common denominator. So I can write this as a single fraction and set the top equal to 0 and set the bottom equal to 0 to identify my critical values, right? I know my critical values for v are when v prime is equal to 0 or undefined. So now I'm going to do my home copy. Yes, and go. Equals 2 pi. Common denominator. This guy needs a root 100 minus x squared over root 100 minus x squared, producing 2x times 100 minus x squared minus x cubed all over root 100 minus x squared. And I know that I can combine some like terms here. On top, this becomes 200x minus 2x cubed minus 1x cubed is minus 3x cubed. Yes? So I get 2 pi times 200x minus 3 x cubed all over root 100 minus x squared. How do we do? Are we okay?
Yeah.
Yes! All right. I know the b has critical values when b prime equals 0 or is undefined. In fractional form, that means the top equals 0 or the bottom equals 0, respectively. So I'll go ahead and consider this constant multiplier is not going to change when it equals 0. Equal question mark 0. Equal question mark 0. Well, if x were to equal 0, then that would be an endpoint in my interval, so that's not going to show up on the middle of my number line anyhow. I know that x were 10, and I have a radius of 10 in my right circular cylinder, which would just be a flat disk, right? And that wouldn't produce it. It wouldn't hold any volume. And so my critical values comes from that when that top equals 0. Because 200x minus 3x cubed over equal question mark 0. You bet your boots. So this is going to happen when 3x cubed, I guess I want to factor out an x, 3x squared minus 200 equals 0. Again, an endpoint. That doesn't do us any good because that's an endpoint, so it won't be in the middle. I just switched the order. I just made it positive 3x cubed minus 200x just so I can factor GCF out more easily, or add to the other side, so whichever you want. Why? Because I like the positive leading coefficient. I do. I know. How does that help us? Well, I hope it helps us, because now I know that critical values occur when x squared equals 200 thirds, which means that my critical values are given by the positive and negative square root of 200 thirds. And that must be 100 times 2, so it must be 10 root 2 over root 3, which is 10 root 6 over 3. Yes? Do I do it? Okay. Yes. You guys made me. 10 root 6 over 3. Oh my gosh. And I dropped the plus and minus. Why did I drop the minus? Well, we're not going to have a negative radius. All right. All that was so we could do this. Do what? So we could do a number line. So I've got my V, this, which form do I want? Probably this form. Yeah, we want to do this form? That's always positive. So 200x minus 3x cubed. And do I want to make it x? So right about now is when I think, analytically, do we want to do this? Or do I want to do second derivative test?
No.
I don't want to do second derivative test. I had a hard enough time getting first derivative, right? So I don't want to do second derivative test this time. But I bet we can power through this because we're stuck. Where is my critical value 10 root 6 over 3? Well, that's got to be 1.4, that's 1.6, so a little bit less than 10, so like 8, so like around here. Okay, so how much balance do we get with our calculator? Well, we're not doing second calculate maximum, second calculate minimum. So if we want to do home screen, right, to get decimal approximations to see where we are, then I think that's totally fine. However, I bet that 1 is less than about 8. So I'm going to pick 1 and still no calculator and see how far we get. If I put 1 here, I get positive times positive over positive, which means that b prime is positive on the interval 0 up until my critical value 10 root 6 over 3. And I'm going to go ahead and do 9. If I do 9, let's see if we have a sign change. Ready? 9, positive. 9 squared is 81. 200 minus, still positive. So I get positive, positive. 100 minus, uh-oh, don't have a sign change. We need to go farther. Is this more than 9?
New factors.
One factor?
Is that 200 minus 3x?
Yes. Good save. Solid. I want you on my team. Minus 3x squared. Yes. Thanks, Danny. See you today. Let's see if my 1 still works. 1 still works. Still positive, 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 positive. Okay. Ready? 9. 9. 9 squared 81 is 80 times 3 is 240. There we go. 200 minus 240 is negative. So I get positive times negative over positive is overall a single negative. Yay! We've got a sign change, which means that a maximum occurs here when radius is this. So max occurs at this radius. Yay! So how do I get my dimensions? Easy. I can let x radius equal 10 root 6 over 3. So x radius equals 10 root 6 over 3, which means that my height equals 2 root 100 minus that squared. Oh gosh. What's that squared? I know we can do it. That would be 100 times 6 is 600 divided by 3 is 66? Oh, I'll take 66 a lot better. That's good. So that's 2 root 34. Is that what you? That's 66. 33 and a third. Thirty-three and a third. Yeah, anytime.
Yeah.
Is this right?
Yeah.
It is? Oh. Now my volume. Oh goodness. Oh geez. It's Friday, right?
Yeah.
So then my volume would be the pi r squared h. So if we wanted to, right, we could do the pi that squared that to get my final volume, but I'm going to do lovely with r. And this is my height. Yes?
Yes.
And then I'm going to do the, ready?
Answer.
We can do it out of the calculator if we want. I feel like I pulled it up. I feel remiss if we didn't go all the way. I'm going to leave the pi out though. 10 root 6 over 3 squared times 2 root, oh gosh, 33 and a third is 99 100 thirds.
100 thirds.
Huh?
100 thirds.
Is that the height? Can we do it? Oh, that's what I got when I did it. That's good. Is it even close? Times pi. That's pi. Oh. Can I grab that one? Times pi. Oh, there we go. So we're gonna do this. Good news is that's what I got already. So math works. If math works 2 days in a row, I'm confident going into our discussion today. Oh gosh. So that would be centimeters, so centimeters cubed. Wow. That was fun. Let's pause it and take care of our housekeeping. So we got our OTL number 4. Okay, so let's suppose that this brought a tear to my eye. So let's suppose that my dad report, and we can see then, what is your dad's job? How old is he? My dad is a math teacher.
Wait, this is so cute.
Daddy, how old are you? Well, super. In 5 years, I will be 4 times as old as you were last year, and 3 times as old as you will be in 6 years. Today we're shifting gears from optimization to related rates. Yes, we've got inflow versus outflow, our classic filling the pool and it's draining out from a valve in the bottom of the tank type things. When we have 2 or more quantities connected, each of which are changing with respect to time in the same problem situation, then we're dealing with the situation that we'll refer to as related rates. Main application of differential calculus. Let's go ahead and take a look at our strategy. This is the same strategy we used last year. Again, the problems have grown in complexity, and the relationships therein could be a little bit more involved. Today, you should have an opportunity to practice towards the end. So we want to read the problem carefully and write down the known rates and the rate we're trying to find. We'll draw a picture and label with relevant quantities. Again, if a quantity is changing, it has to have a variable. We'll write a formula that relates the quantities in question, try to limit those variables only to the rates that we're dealing with. That will help eliminate excess stuff. Now I'll differentiate both sides of my equation with respect to time. That's the difference. So it's like implicit differentiation because every time I differentiate an A for area, it's going to spit out a dA dt in accordance with the chain rule. Every time I differentiate an R, right, the radius, it's going to spit out a dr dt in accordance with the chain rule. And that's similar to implicit differentiation. Then we'll solve for the desired quantity last. Only then will we plug in that moment in time data, right? Otherwise, if we plugged it in too early, we'd lose our changing variables and we'd lose our rates. So let's go ahead and take a look at a couple. So this is a classic problem that's shown up most recently on the multiple choice portion of the exam. A 6-foot tall man walks away from a 15-foot tall street lamp at a constant rate of 5 feet per second. How fast is the length of his shadow increasing when he is 40 feet from the street lamp? So let's go ahead and read the problem carefully, write down the known rates, and then the rate we're trying to find. So a 6-foot tall man walks away from a 15-foot tall street lamp at a constant rate of 5 feet per second. How fast is the length of his shadow increasing when he is 40 feet from the street lamp? All right, so to help, I went ahead and I love clip art, so I've got a picture here, and we can go ahead and start labeling with variable quantities and our constant quantities. Keep in mind, if something is changing during the course of the problem, it has to have a variable in your picture. The moment in time values, that snapshot, the moment in time values will only be plugged in at the very end after you've isolated for our stuff. So let's go ahead and write down our known rate and the rate we're trying to find. Our known rate. And we want to find. All right, so what do we know? We know that he's walking away from the street lamp at a constant rate of 5 feet per second. And so I've got that. We want to know how fast the length of his shadow is increasing when he's 40 feet from the street lamp. So it looks like I'm going to do that horizontal distance from the street lamp to the man could be a distance of x. Is that changing over the course of the problem? Yep. So we have to label with our variable x. What else is changing? And we're trying to figure out is length, the rate at which his shadow's increasing. So we need a variable for our shadow distance as well, and I'll call it y. Now we can go ahead and write our known rates and what we're trying to find. So based on our picture, right?
Bless you.
Based on our picture, what's our known rate with likeness notation? Bless you. What's our known rate here? Danny?
He's 108.5 feet per second is the fastest one.
Good. So in terms of my picture, which variable would that be represented by?
That'd be d over dx.
Almost, yep. It would be dx over dt, the rate of change in the horizontal distance with respect to time. Good, thank you. So dx dt, from our likeness notation, we're going to be differentiating with respect to time, y units over x units. In this case, x is that changing quantity. Good. What do we want to find? We want to find how fast the length of his shadow is increasing when he's 40 feet away. So what are we trying to find in terms of my picture? Right? Grace?
dy dt.
Good. So we're trying to find dy dt at the instant when what equals 40? When he is 40 feet. So which variable would that be? When x equals 40? Awesome. All right. I think we have enough now. So 1 and 2 we've kind of done together. We've drawn a picture and labeled with relevant quantities. If the quantity is changing, it has to get a variable, right? Next, we've written down our known rate and our unknown rate. Now we'll go ahead and write a formula that relates to the quantities in question. I'm going to try to limit the variables in my formula to only those quantities that are changing. So let's go ahead and take a look at our picture. How can I write a formula that relates to those quantities in question? Well, I haven't completely labeled my picture. I know that I do have some constant things, like, right? What else could I label in my picture? Vivian?
Can you go back to the picture?
Yep.
The guy would be 6 feet.
Okay, so is that changing throughout the course of the problem? No, so we can label that with a number. That's good news. And good, thank you. And is there anything else we can label in our picture, Sydney?
The straight lamp,
Is
15 feet.
that changing throughout the course of our problem? No. So we can get that to, did you say 15 feet?
Mm-hmm.
Awesome. We've got enough. Let's go ahead and write an equation, a formula that relates my variables in quantity that are a part of my rate. So I need an equation that has x in it and y in it, because when I differentiate that with respect to time, I'll spit out my known and unknown rates. So what equation could we come up with? Oh gosh, I don't know. Maybe we'll just skip on to the next one because it's Friday. I mean, it's Friday. It's Friday!
No. We can do it.
We can do it.
Yeah.
How about that?
Yeah.
Oh, now a relationship exists between little triangle and big overall triangle. We've got similar triangles, right? We know that we can write a proportion that relates to those changing quantities. I would say y is to 6.
Similar.
Similar triangles?
Yeah.
Yes. What did I say?
You said somewhere, she said.
Oh, yeah, similar triangles, because they're same exact shape but different size. How about little triangle is to little height, so little base is to little height, just like big base is to big height. What would my big base length be given by in terms of my variable quantities? Kobe?
X over 15.
Oh, so little triangle is to little height, just like big triangle is to big height. So my whole x plus y, good. All over 15. Nice. So everybody see we've written a formula that relates my variables, right, that are eventually become my rates? Yes! Sweet house. Okay, now what do we want to do? Try to limit those variables in my formula to only those quantities that are changing. I think we've done that, right? Both x and y are changing. We need both x and y in my equation. We're going to differentiate both sides with respect to time, similar to implicit differentiation. However, it might be useful to See if we can't rewrite that and write a single y term, because every time we differentiate, we'll spit out dy dt. So while we're still here, I might multiply both sides by 15 over 15. And 6 over 6. In order to clear the fractions. Yes? Combining like terms by subtracting the 6y over gets me 9y equals 6x. Yes? You guys okay? And now I think we're ready. Let's differentiate both sides with respect to time. So by differentiating both sides with respect to time, we'll get our rates involved. What's the derivative of 9y with respect to time? 9 dy dt. The derivative of y with respect to time is dy dt. What's the derivative of 6x with respect to time? 6 dx dt. Okay.
Nope.
All right. And now we need, what are you trying to find? Dy dt? So dy dt is right here. And that's given by 6 dx dt all over 9. Is that what you guys are reading? So now we can plug in our known rate and figure out our unknown. What's about the x equals 40? Is that not needed? Is that shadow line changing the same the whole time? Seems to me like we should be going faster when it's farther away, doesn't it? I'm going to be a comebacker. 6 dx dt is 5 feet per second over 9. So I get 30 ninths. Dividing out a 3 from top to bottom gives me 10/3. And a label on dy dt would be what? Feet per second. That wasn't bad. Although I'm getting a little red flag with that x equals 40. It seems like his shadow should be increasing at a different rate depending upon how close he is to the street lamp, to me. So that's a comebacker. Let's come back and check it. I do like the picture though. Pretty sweet. All right. For now, that's good. Let's take a look at another. Oh, there's our space. Let's suppose that a hot air balloon is rising straight up from a level field and being tracked by an inclinometer 500 feet from the liftoff point. At the moment, the inclinometer's angle of elevation is pi over 4 radians. The angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? So we want to read the problem carefully, write down the known rate and the rate we're trying to find. To do this, we can draw a picture and label with relative quantities. If a quantity is changing, it needs to be labeled with a variable. So I went ahead and got this nice little picture. Notice how our inclinometer is a set distance away, right? Is a set distance away from the takeoff point. And so we can put a constant there, 500 feet. However, the height of my balloon and the angle my inclinometer is registering are all changing in my right triangle. So they have to have variables. Do you see? Now we can go ahead and write down my known versus unknown rates. Okay. So what's my known rate? Right? What's my known rate here based on the variables I've chosen to use to label in my picture? What's our known rate here?
Theta.
Sid?
Theta.
theta, right? Theta is our angle the inclinometer measures, but our known rate is
D theta dt.
yes, in like this notation, very nice. So we know at our moment in time, d theta dt equals 0.14 radians per minute. Was that right? Next, what are we trying to find? So what is it we're trying to find in Leibniz notation? Riley?
Define d8 dt.
Yeah, we're trying to find how fast the balloon is rising at that point. So we're trying to find dh dt at the instant when the inclinometer's angle registers power 4 radians. This problem's rad. All right. Next, we're going to write a formula that relates the quantities that are in my rate. So I need a formula that relates theta and h. Everybody go ahead and take a look at your triangle and talk with your partner to come up with a formula that relates theta and h. All right, so what formula are you guys using? What formula are you guys going to use? Kobe and Sophia?
So the height equals 500 tangent theta.
So hang on, let me catch up with you. So you're using tangent. I have to do one step. It's take a step, drag Mr. Fritz, take a step, drag Mr. Fritz. So tangent of theta is given by opposite over adjacent. So tangent of theta equals opposite over adjacent. Okay. And you're saying that h, height, is given by 500 times tangent theta? Awesome. Who saw the same relationship? Raise your hand. So who all the same relationship, everyone with tangent? Cool. So now we've got a formula relating the quantities that are in my rates. What do I need now? I need to differentiate both sides with respect to time. So we'll differentiate both sides with respect to time, and that'll generate our rates. So the derivative of h with respect to time is dh dt. The derivative of 500 tangent theta with respect to time is constant multiplier, 500, still there, times. And what does tangent differentiate to? What does tangent differentiate to? Grace?
Secant squared.
Awesome. Secant squared theta. And then times the derivative of the angle. The derivative of theta with respect to time is d theta dt. So notice how this is similar to the technique implicit differentiation. Every time we differentiate a variable term with respect to time, it spits out a d theta dt, or a dr dt, or a dh dt in accordance with the chain rule. What do we want? We want a dh dt when theta equals power 4 radians. And by golly, we already have dh dt isolated. So we're ready to plug and chug. Let's do it. 500 secant squared and 0.14. So when pi over 4 is the angle measured on the inclinometer, we know that that's a 45-degree angle. Therefore, our secant ratio is given by hypotenuse over adjacent, right? Because secant is the reciprocal of. So if this is 500, right? 500, because pi over 4 is a 45 triangle, which means this would be 500 root 2. Would be the hypotenuse. At that instant, you guys agree? 500 root 2. Therefore, my secant, right, would be adjacent. I'm sorry, hypotenuse over adjacent would be root 2. Those guys getting root 2? So secant squared would be 2. So I'm getting 500. So I'm getting 500 times 2 is 1,000 times 0.14. Worked out too nicely. Right? Which equals what? 140? And a label? Feet per minute. Dang. I like that picture. It's a cute little balloon. Shall we compare? Oh! Check it out. Bam. Boom. Slam. Ka-chow. I like that. Oh my gosh. You guys are great. No, you are. No, you are. No, you are. Don't say it out loud. Just write it in. When solving a related rates problem, all terms are differentiated with respect to blank in a process similar to blank blank. When labeling a picture, when is it okay to label a quantity with a number instead of a variable? Ooh, that's very important. I like that question. And if too many variables exist in your formula, which do you try to eliminate? Oh, that's a good one too. Think about which ones we need. Okay, I know that we have some anxious students who are vying, right, for the chance to share number one, to fill in the blank. But I'm going to go ahead and let Sydney do it because I know she's going to teeter out of her seat if I don't let her go. So when solving a related rates problem, alternative differentiation with respect to Sydney.
Time.
Oh, yeah. In a process that is similar to Sydney.
Implicit differentiation.
You win. Oh my gosh. Yes, very nice. Did he get it away when I made this blank a little bit longer than that blank? Oh, it's a struggle. It's a battle, daily battle. When labeling a picture, when is it okay to label a quantity with a number instead of a variable? So when would that be okay? Danny?
It doesn't change over the course of the problem.
Yeah, only when it's fixed over the course of the entire problem. Over course. That's a single word. New compound name. Fixed over entire problem situation. It's the only time we were allowed to label a quantity with a number instead of a variable. If too many variables exist in your formula, which should you try to eliminate? We didn't really do this today, but our focus and drive for the problem includes, right, the variables that are in my rates. So if I have h's and thetas, but my equation includes r's, I would try to get rid of r's. You see what I'm saying? Right? So we want to make sure that we keep the variables in my formula that are present in my known and unknown rates. We can eliminate those quantities that are not in my known rate or rate that I'm trying to find. So let's see. If too many variables exist in my formula, which should you try to eliminate? The ones that are not in your known and unknown rate. That you wrote down at the beginning. Guys, great work. ROTL number 5, did I get it? Did it fit? Is this printable? I started to make it even number. Okay, so it looks to me like, bam, you got a great Friday where you have an opportunity to work together. I want you working together, right, so that you can be talking about these sums together on our first day back with related rates. We got 2, 3, 7, 3, 9, 11, 13, 19, 21 out of 6. So again, a shorter assignment, but some of them take a little bit longer, okay? I'm going to go ahead and stop the recording and then upload this to our Moodle site. Good work today. Please work together.